Hello, welcome back. Now we're going to actually develop a DP algorithm. We're going to talk about one example, in particular, rod cutting, and then we're going to see how we apply dynamic programming to solve this problem. So originally this was one video and turned out to be very long. So I decided to cut it to two different shorter videos. So sorry, that's why it's taking too long to make these videos. But yeah, it's ready now, hopefully. Let's go through it. So what have we done so far? We talk about optimal substructure, and we also talk about overlapping subproblems. If we can show that our problem have these two, then we can use dynamic programming. So we spent a bit of time talking about overlapping subproblems in the first lecture, and I think that's pretty straightforward. You should know what it's about, right? And optimal substructure, we spent a bit more time on that in the second lecture, and I think this is a harder concept to grasp, but hopefully you get some idea from the previous lecture. And now we're going to see these two things again with something concrete, with the rod cutting example. Okay, so the steps that we're going to take, I'm going to base this on the textbook. So you go read page 359, CLRS. They talk about 4 steps. 1, characterize the structure of the optimal solution. 2, recursively define the value of the optimal solution. 3, compute the value of an optimal solution. I'm just reading the list here, so that's pretty boring. You can read the list, right? These are the 4 things that they have on the textbook. I'm going to follow that almost exactly. So the first thing I have to do is to translate that, or try to translate that into a more informal English. So here's what I came up with. Step 1. Show that the problem has optimal substructure. This is what we talked about in the previous lecture, and this time we're going to do it again with something concrete, so hopefully it'll make more sense. Step 2, show the recursive relation that gives the optimal solution. What I mean here is, if we want to solve a problem using dynamic programming, then we have to split the problem into different subproblems, right? And we do them recursively. That's what we talked about in the previous lecture as well. So now I have many subproblems. How do I pick the one that will lead to the optimal solution to the problem? So you have to define this relation. And to me, this is the hardest step, right? Which subproblem do I choose, basically? This is hard because it's different for different problems, right? And basically every time there's a new problem, you have to work out what the relationship is. But once you get this done, you will be able to write the code. Okay, we're going to see that with the example with rod cutting. Step 3. Once you have written the code, once you know the recursive relations, you can compute the value of the optimal solution. Now, I put value there in capital letters because in optimization problems, your answer usually consists of 2 parts. 1 is the value of the solution, just the value, and 2 is the actual combination or the strings, whatever, that will give you that optimal value. For example, take the longest common subsequence. You can just give me the length of the longest subsequence. So I give you 2 different strings, and I ask, what's the longest common subsequence? Well, you can just say, well, the longest common subsequence length is 8, just number 8. And in fact, that's what we did in the first lecture when I talk about longest common subsequence. Remember, we build up the solution. We build up the table, starting with zeros on the bottom row, zeros on the rightmost column, and then we build it up to the top left corner when you get the number. And that number there, it just tells me the length of the common subsequence, the longest common subsequence. It doesn't actually tell me what the subsequence is. To do that, you have to do extra work, and that's step 4. You got to find the combination. You got to find the strings that will give you that is the longest common subsequence. And you have done this in COM25, COM2010, which is why I didn't go through it in the video. So I'll leave it to you to revise. What you have to do is not that hard really. You traverse the table again from top left and go into the bottom right. And we can probably do this in workshop. You can ask me in the workshop to do that. Yeah, we can discuss it there. But anyway, for this course, step 3 and step 4 is kind of the same, because if I ask you to do something using dynamic programming, then I expect you to give me both the value and the combination. Okay. Okay, so let's now talk about the problem. Rod cutting. Pretty much this whole lecture is going to be about this problem. Actually, this one and the next one. So make sure we understand the problem well. I'm going to talk a bit about the problem. We're going to analyze it. So we have one piece of rod that we can cut into small pieces. And don't worry about the cost of cutting the rods, right? Now, different length of the rod can sell for different prices. So if I give you a rod of length 10, you can cut it up like 5 and 5, 3 and 3 and 3 and 1, 6 and 4, up to you. So you can see the prices for different lengths here, right? Now, the question is, if I give you a rod of length 10, how should you cut it up to maximize your revenue? What if I give you a rod of length 8? What if I give you a rod of length 6? And so on. Should you cut it up? How should you cut it up? Maybe you should not cut it up. Don't know, right? So that is the problem. And I'm going to show you that if we brute force this, you're going to have exponential complexity. But we will also see that we can find overlapping subproblems. And then we can also have optimal substructure, which means we can use dynamic programming. So that's what we're going to do. Let's start by looking at how many combinations that we have. Okay, so let's say I have a rod of length 4. Here's all the breakdown that I can have. I can either not cut it. I can either cut it with length 1 and length 3, or 2 of length 2, length 3 and length 1, and so on. These are all the possible ways I can cut the rod. So here you can see that the best way to cut a rod of length 4 is to cut it into 2 different pieces of size 2 each. That will give you $10, as you can see here. But I just want to give you an idea that there is a lot of combinations. Like these are all the combination of rod of length 4. What if you have a rod of length 8? Then you can break it down into 2 rods of length 4. And then we can break this down further into like different sizes, as you can see in the previous page. And even more, you can actually break down a rod of like length 8 into 2 pieces of length 2 and length 6. And then you can break this down even further. Length 6 there's a lot more combinations of length 6. In fact, there are so many combinations that I'm not going to even try to do an example with rod of length 8. We're going to do something with rod of length 5. Okay? If I only make one cut on a rod of length 5, these are all the cuts that I can make. If I make another cut, so if I make 2 cuts, these are all the combinations. Right? So you can see how this kind of explodes a bit. Now, what if I make one more cut? How many more combinations do I have? Well, these are all the combinations with 3 cuts, actually just 4 of them. And of course, you can make 4 cuts. That'll give you the case of 1, 1, 1, 1, 1. Right? So, look at the numbers again. You got 1 way to not cut it. You got 4, like making 1 cut, 6 to make 2 cuts, 4 to make 3 cuts, and 1 to make 4 cuts. 1, 4, 6, 4, 1. Does that number ring a bell? That's actually the way to choose n items out of 4. right? If you have no cuts, right, there's only one way to do it, 4 choose 0. If you cut one place, there's 4 choose 1 ways of doing it, because there are 4 places where you can cut. If you want to cut in 2 places, there are 4 choose 2 ways of doing it. So there are 6 ways, and so on, with 3 cuts and 4 cuts. This is just combinations. So if n equal to 5, if you have rod length 5, then you have 4 possible places to cut. So if you give me a rod of length n, you have 2 to the n minus 1 possible combinations. So if you try to brute force this, that's your complexity. It's going to cost you 2 to the n. So definitely not something that you want to brute force, because this is exponential in complexity. So how can we do better? Well, we're going to use dynamic programming. But with dynamic programming, you gotta be able to see the problems and the subproblems. And then after that, you gotta see if there are overlapping subproblems. And sometimes this process is not that easy. Like if you want to, you can think about this rod of length 5. And you can try to do this yourself without listening to this lecture for now. This is your original problem, a rod of length 5. How do you break it down into problems and subproblems, right? Just pause the video, just think about it. Okay, so some students, this is what they did. They say that here's your original problem, rod of length 5, and your subproblem is everything. So I can either cut in 1 place, or I can cut in 2 places, or I can cut in 3 places, or 4 places, whatever. It's like your tree is basically this guy on top, and then the next level is everything else. So that's not how you do it. Yeah, that is breaking down the problem into subproblems, sure, but then you'll have so many subproblems, it's pointless, because that's just doing brute force. And number 2, nothing's overlapping. So what's the proper way of doing it? Well, let's think about it a different way. So here I have the original problem, and I'm gonna say the first level of subproblems is where I cut it in just 1 place. Now, once I cut in 1 place, I can do another cut, right? So if you look at the options that we have here, well, there are 6 of them. So how are we going to relate these 6 outcomes with the first 4 that we have here? Well, let's look at the first cut here. Like I got 1 and 4. If I cut the left one to one piece like that, then surely I can't get all the combinations, right? So I can come up with this one here, 1 1 3, 1 3 1, or 1 2 2. I can't come up with 3 1 1, 2 1 2, or 2 2 1. Okay, so we see now that we're kind of limiting our subproblems here. So here's what we have. These are the 3 that I can have. What about the rightmost guy here? If we make one more cut, how many subproblems do we have? Well, actually, we see that you have these 3 subproblems, and voila, overlapping subproblems. Actually, now that I think about it, we have only 5 here. 1 2 3 4 5, but we had 6 before. So what happened to the last one? Well, that's this case here, right? And that can only happen if you do these 2 middle cases. Oop, and no, the dog is not coming back, at least not yet. But anyway, these are the these 2 middle subproblems here. They will reduce down to this one. They both have there's an overlap, but of course you can also reduce down the middle to 2 other subproblems. So all the green arrows, if you can track it. And of course they all reduce down to the simplest subproblem. Eventually you hit this 1 1 1 case. Anyway, this is complicated. This is a mess. This is actually, this looks a bit like art, but we're doing computing, we're not doing art, so don't worry about this. We're not going to break down our problem into this mess here, we're going to have a new rule. After each cut, you do not cut the leftmost segment any further. So I made one cut, like 1 and 4. I'm not going to cut the left one any further. Well, that doesn't make sense because I only have one piece here anyway. But if I have 2 and 3 here, I'm not going to cut the left one any further. I'm just going to fix that to be 2. Why am I doing this? Why am I doing this? Because of symmetry. So if I cut 1 and 4, I can end up with 1, 1, 3. So that's the same thing if I'm cutting 2 and 3, then I cut the left one, I'll end up also with 1 and 3. And because they overlap, I'm not going to do this. Simple as that. Okay. So does the tree look different now? Sure. And this is what it looks like now. So see how in every subproblems I leave the leftmost segment uncut. So, well, obviously with just one on the leftmost side, just no, you can't really cut anymore. But here, if the leftmost segment is 2, then my subproblem is going to be 2, 1, 2 and 2, 2, 1. I'm not going to cut the leftmost any further. Same with 3 on the left hand side. In fact, I can only make one cut, 3, 1, 1. And even with the 4 and 1 here, there's no more cuts to be made. That's it. So where are the overlapping subproblems? Can you see it? Is it this one and this one? Well, actually, no. Those are not subproblems. Why? Because if it's on the leftmost side, then I won't cut it anymore. So 4 here just will stay as 4. Whereas the 4 on the left-hand side here, that would be cut up into more and more pieces. So if you want to look for subproblems, look at this one here, the 3 and the 3 here. Right? So you see how this one here, I'll recurse further. I can cut the 3 into 1, 2 or 2, 1. But that's the same cuts that I will make with the 3 on this problem here. Because I'm gonna recurse a bit further, I'm going to cut into 2, 1 and also 1, 2. That's the same problem. Now, this 3 down here, that's not an overlapping subproblem, because why? The rule is the leftmost ones, we're not going to cut anymore. So that 3 will stay as it is. We're not going to go any deeper. Okay, so hopefully you can see where the overlapping subproblems are. So we've done 2 things here. 1, we significantly reduce the complexity of the tree by using that simple rule. And 2, we also identify where the subproblems are. Sorry, we identify where the overlapping subproblems are. So these 2 here. So that's good. Now our game plan. What we want to do is, because we're not going to cut the leftmost segments any further. That means we're going to find the optimum price when we have rod length 1, length 2, length 3, and so on. And this is not the same as finding the price of a rod of length 1, length 2, length 3, and so on. So in fact, this diagram, if you notice, I added one more part here. So if I have a rod length 5, actually I have 5 options. I can make what? Well, when I make the first cut, and I can either be in position 1, position 2, position 3, position 4, or position 5, as in no cuts. Right? And this one here, the rightmost one, I'm not going to cut up any further. So the value I get from this is the value I get from the price of having a rod of length 5. Whereas with these ones, they're different, because these ones I have to recurse. So that's the difference between the 4 on the first subproblem here and the 4 on the 4th subproblem. See, the 4 here, when you eventually return, you will get the optimal price of a rod of length 4. Whereas this one here is just the price of a rod of length 4. Right? Make sure you understand the difference. Here, and the 3 here, you're going to work out the optimal price of a rod of length 3. Same as the 3 here. But the 3, this one, on the 3rd subproblem, this is just the price of a rod of length 3. So just one more time, the optimal price that you can get for a rod of length n is not the same as the price of a rod of length n. So the example here is rod of length 4. Okay, so the top table here, that gives you the price. If you sell something of length 4, you can get 9. But if you cut into 2 different pieces, you can get 5 and 5, right? You'll get 10. That's the optimum value that you can get. So you can check with 5, check with 6. I haven't worked out what these are. So you can try to work it out yourself, see if they're different or see if they're the same. I'm pretty sure 7 will not be the same because, as you can see, you get 17 if you sell a rod of length 7, but you can make it, at least you can make 6 and 1. That'll give you 18, right? So that's at least that one is better. Anyway, great. We worked out the problem and subproblem structure. We also worked out what the overlapping subproblems are. We recognize it. Now what we have to do? We have to show that the problem has optimal substructure. And how do we do this? You have to show that the optimal solution to the problem will contain the optimal solutions to the subproblems. Again, that's the definition of optimal substructure that we're using, and this is what you have to show. All right, let's try to make sense of optimal substructure again using this example. You have a rod of length 5, and you're going to see how much money you can get out of it. To work that out, you have to make a choice. I'm going to make one cut. Where am I going to make that cut? Okay? And whatever choice you make, it may lead to more choices. It may lead to more subproblems. Now, you have to show that the optimal solution to your problem, the one up here at the top, must contain the optimal solution to your subproblems, which is all of these 5. Right? These are all your subproblems, and you apply the same algorithm, you apply the same technique to work out the optimal solution, right? Well, to work out the solution, and you have to say that if I apply it on this rod of length 4 here, then the answer I get, the answer that I use, must be optimal. Of course, I still have got to choose of one of these, but that's later. That's talking about recursive relationship, and that's in the next lecture. For this one here, you just have to show that the optimal solution must contain the optimal solution to the subproblems. So how do we do that? You have to prove it using this technique. There's like a procedure that you got to do. This is a proof by contradiction. So we're going to start by assuming that we have the optimal solution. So I already have the optimal solution. I know which path to follow. You know, like in the search tree, I know which subproblem is going to contribute to my optimal solution. And we can show that we are using the optimal solution to the subproblem that we're using. So let's say I have the optimal solution of cutting a rod of length n. Let's just say length 4. So if I know the optimal solution of cutting a rod of length 4, that means I have looked at all the subproblems. Cutting rod 4 can be broken down into, let's say, 1, 3, 2, 2, 3, 1, or just 4, no cuts. So I look at all the solutions and I know the best one. Let's say y. Let's say 1 to 2 is that's the best I can do. So that's my optimal solution is going to be y plus x. So y is the value I get from a rod of length 4, and x is just the value of just rod of length 1. So my optimal solution for this problem is just x plus y. Okay, so everything else here is times y. Now I want to tell you that this y here must be optimal. So the best I can do, like this is a solution here for the subproblem of cutting the rod into 2 and 2. The result that I get, y, must be optimal. Because why? Why if it's not optimal? Well, if that's not optimal, right, that means I can find another solution z. and Z is better than Y because I mean it's better. It's Y is not optimal, so there's something better, and let's say Z is better. So that means the optimal solution to the whole problem is not X plus Y. It's actually X plus Z because that's better. So that's a contradiction because we assume that the solution to the subproblem, the solution to the problem is X plus Y. That's our assumption, which means that Y must be the best solution for this subproblem here and must also beat all the other ones. But anyway, if you just look at the best subproblem that we choose, Y must be the optimal solution. So we must have the optimal solution to the subproblem. And that's pretty much it. Make sure you understand the logic. And because we're going to do something similar next week with the greedy algorithm, we're going to use this proof by contradiction again. Okay, let me repeat that fact. We assume that we have the optimal solution. Don't worry about how did you get it. It doesn't matter. All that matters is you have the optimal solution for the whole problem. So what I'm claiming is that if you have the optimal solution to the problem, then you must have the optimal solution to the subproblem as well. Because if you don't, you can come up with a better optimal solution for your problem. All right? So your optimal solution, you claim this is best, but when you look at the subproblem, the one that you have is not optimal, so you can find something better. Automatically, that will mean your solution for the whole problem is wrong because you can find something better. It's not, I mean, whatever you have is not optimal anymore. That's a contradiction. I guess here's another way to think about this. Maybe it can help. If I claim that I have the most expensive computer in the world, then all the parts in my computer must also be the most expensive part in the world, right? So I can't say like, oh, I have the most expensive computer in the world, but my monitor is not the most expensive monitor in the world. Then that means that I don't have the most expensive computer in the world because I can find a monitor which costs more than what I have right now. I add it up to my computer setup, then I will have something which is more expensive. So I can't claim that I had the most expensive computer in the first place. That doesn't make sense. That's a contradiction, right? That's what you're doing with optimal substructure. It's actually very simple, but it seems that some students in the past they have problems. So I hope that helps. I mean, this is what if you think I'm going a bit too detail about this, sorry, but I just want to make sure that everyone understands what optimal substructure is. So yeah, generally that's a step, right? You show that if you have the optimal solution to the problem, then you have to do one or more subproblems. Then you assume that you have the optimal solution, and then you argue that the solution to the subproblems must also be optimal. Because if it's not, then I can do this cut and paste technique. So that's a terminology they use in CLRS. So cut and paste means I cut the better solution for the subproblem and then paste it. And then voila, I will have a contradiction because that's a better solution than the one that we said is optimal. So that's my attempt of explaining this optimal substructure. If you want something more terse, something more detailed, then you can refer to the textbook, page 379. And for the rod cutting, here's a better write-up for it. I'm not going to bother reading all this again. It's there for you. It's just a repeat of what we did earlier, basically. But this is something that you should write when you get asked to show optimal substructure. Well, you probably need to you probably need to write more than this because I have to fit all this in a slide, right? And yeah, we can do more during the workshop as well. So that's it about optimal substructure. But remember, there are 4 steps. 1, show that there's an optimal substructure. That's what we just did. And then there's step 2, 3, and 4. And I kept saying that step 2 is the hardest one because it is. But the nice thing about step 2 is it's hard, but you know how to do it. Whereas step 1 is like a new concept, this whole optimal substructure. And this mathematical language may confuse you a bit, but hopefully I demystify the whole optimal substructure thing. All right, we're gonna do the rest in the next video. And it should be simpler, hopefully. Okay, so I'll catch you in the next video. All right, cheers.